In this video, I'll go over the concept of total numerical error. This concept first arises now as we're talking about numerical differentiation, but it expands and is generally applicable to solution algorithms for differential equations as well. After studying this video, you should be able to understand why higher order finite difference formulas are commonly used and understand the inherent trade-off between truncation error and round-off error. Make sure that you understand the idea of truncation error from the numerical differentiation video before moving forward with this video. So one question that might have arisen as you watched the numerical differentiation video is, why do we need these higher order formulas? Why not just reduce the step size of a first order approximation to get accuracy? So if we have a first order finite difference where we take df dx is equal to f of x plus h minus f of x over h, that's, recall, a forward finite difference. It'll have a truncation error that's proportional to h and the second derivative of f. And we know if h is small enough, then the approximation nears that limit where h approaches 0, which would be the definition of the exact derivative. So a natural thing to think is, well, why wouldn't we just make h really small? We have a computer and plenty of processing power and use that to get our exact derivative. Why do we need to come up with things like that fourth order centered finite difference approximation that's a much more complicated formula? And the answer to that is because as h gets smaller, round-off error can grow to dominate the result. So in this video, we're going to see why that happens. So let's look again at that first order finite difference. So we'll call that f prime approx, and it's equal to f of x plus h minus f of x divided by h, and then we'll have the truncation error proportional to h, which is a function of h, and f double prime. So when we calculate this with double precision on a computer, we introduce a second source of error. So we would have f prime approx, which includes some truncation error. So that's error that has arisen because of approximations we made in developing this algorithm for the forward finite difference. And now we also introduce round-off error. And that round-off error is going to be a function of x and h, just as we always have round-off error anytime we evaluate a numerical function on the computer. So we'll call that round-off error would be the round-off error from the function evaluation. So this would be from the function evaluation of x plus h, and round-off error from the function evaluation of f of x. So now we've got two sources of error, and we'll call this the total numerical error. We have round-off error, which is coming from implementing on a computer with finite precision. And we have truncation error, which is from the algorithm itself and the approximations we made truncating the Taylor series to develop the algorithm. And in this case, they're both proportional to h. So that truncation error again, so the truncated term from the Taylor series, if you recall, was 1/2 h times the second derivative, and this would be the maximum second derivative in the interval. And the round-off error from the previous slide is the round-off error from evaluating the function at x plus h minus the round-off error from evaluating the function at x, all divided by h. Now we know that maximum round-off error for each function evaluation is going to be the machine epsilon, which is 2.2 times 10 to the minus 16. So we can use that to find our maximum round-off error, give that an upper bound. That's going to be, we can imagine this one will be less than or equal to epsilon, and this one will be less than or equal to epsilon. And this could be a negative epsilon, this could be a positive epsilon, so we've had positive minus minus, so the total maximum error here would be less than or equal to 2 epsilon. So our maximum round-off error would be epsilon plus epsilon over h, or 2 epsilon over h. So we have our truncation error, which is proportional to h, and our round-off error is a function of h, but it's actually proportional to 1 over h. So we can use that to look at the behavior of the total numerical error. So as the step size h is decreased, the truncation error decreases, but the round-off error increases. So here's a graph that illustrates this behavior. So we have log of h on the x-axis. So as h goes down, we see the round-off error is increasing, and the truncation error, as this upper line, is decreasing. So that is ET, and this is E round. And eventually we get to a point where the round-off error actually dominates the total error, and the truncation error, as we keep reducing h to try and reduce the truncation error, we hit this point of diminishing returns, and the total numerical error is not driven by the truncation anymore. The total numerical error is driven by the round-off error. And that's not desirable because that round-off error, recall, is unpredictable. We can get a maximum bound on the round-off error using this analysis with epsilon, but we can't really predict how that's going to behave as we change the step size in the solution. So we really would like to be, in general, operating up here. If we operate up here above the point where the round-off error starts to dominate, then we get predictable error behavior. We know if we reduce h for a first order method that the error will roughly reduce in half. So we can figure out where is this kind of cutoff, call this h min, by looking at the total error. So we know that the total error, the maximum total error, is equal to or less than or equal to the truncation error plus the round-off error, where the truncation error is hf double prime over 2, and the round-off error we've shown is 2 epsilon over h maximum. So we can take the derivative of that and set it equal to 0 with respect to h to find that minimum step size, which is the local minimum on this curve that we're showing here in black for the total error. So we take that derivative, set it equal to 0, so we get f double prime max over 2 minus 2 epsilon over h squared, that's the dEdh. Solving for h min, we get 4 epsilon over f double prime max, take the square root. And this gives us, if we solve for h min, recall epsilon is 2 times 10 to the minus 16. And for this analysis, it's just an order of magnitude analysis, we'll just call that 1. It's some constant. It's not going to have a major effect on the solution here. And we get a minimum step size, that point, about 3 times 10 to the minus 8. So that we wouldn't want to reduce h any further than that, because we would hit that point of diminishing returns and the round-off error would grow. So that seems pretty small. You might think, well, why not just do that? Well, let's look at what happens with a higher order finite difference formula. So here's the fourth order center difference. And looking at that fourth order center difference, we see we have 4 function evaluations. So we'll put in our epsilon for each of those 4 and assume that to get a maximum bound on the round-off error, we'll assume that the round-off errors are negative or positive to maximize that numerator. So we get epsilon plus 8 epsilon plus 8 epsilon plus epsilon, all divided by 12h, or 3 epsilon over 2h. But the truncation error now is proportional to h to the fourth and the fifth derivative, because that's the lowest order term of the Taylor series that is truncated in order to develop this finite difference approximation. So our total error changes primarily with this h to the fourth. And we can go through the same thing that we did before. Take dE dH, set that equal to 0, and that gives us an h min, again just using 1 for the fifth derivative, an h min of 1 times 10 to the minus 3. So now we have a much larger step size, and what this means again is if h min is less than 1 times 10 to the minus 3, then we're going to start having some serious round-off error concern. So now we're at a larger step size, so you might think, well, what's happening with this graph? Aren't we just increasing the error? Aren't we up here? But really what's happening is this is the point that's moving. And the way that that's moving is the overall point, the total error, is it's moving down and it's moving to the right. So we're getting a smaller total error at a larger step size is the difference. And we can see that here on the next slide, how the fourth order actually is more accurate. So if we take that first order finite difference, so the minimum h is 1 times 10 to the minus 8. So our truncation error, so remember that means our truncation error is defining the error. Our truncation error is going to be 1 times 10 to the minus 8 times f double prime. For the fourth order finite difference, we had 1 times 10 to the minus 3 for h min. So our truncation error, which is h to the fourth times the fifth derivative, is 1 times 10 to the minus 12. So we have a difference here of 4 orders of magnitude in accuracy. So much better. And another side note is this is proportional to the fifth derivative, and that's typically for most functions, unless it's an oscillatory function, that fifth derivative is going to be much less than the second derivative. So with a higher order approximation, that larger step size, 1 times 10 to the minus 3, is much more accurate, and it's also going to be much more computationally efficient. It will take us a lot fewer steps using a step size of 1 times 10 to the minus 3 to take the derivative of a function over some range versus using a step size of 1 times 10 to the minus 8. So we have two major benefits of going to the higher order differentiation scheme. One, it's more computationally efficient, and two, it yields a much more accurate result. So let's just go over some conclusions of this analysis. First of all, we can't indiscriminately reduce the step size of a lower order finite difference formula because the error may become dominated by the round-off error. And the problem with the round-off error, again, is it's unpredictable. We like to have some understanding of what is happening with the error behavior of a numerical algorithm that we're implementing. For example, if it's a first-order method, we want to know that if we reduce h in half, that's going to cut the error in half. Or with a fourth-order method, if we reduce h in half, that's going to cut the error by 2 to the fourth, or cut the error by a factor of 16. So as the order of finite difference approximation is increased, we know that truncation error scales as h to the n. So a fourth order method would scale as h to the fourth, but the round-off error still scales proportional to 1 over h. So that's what leads to that result where as we go to a higher order method, we have a larger h yields a smaller total error, which is mostly dominated by the truncation error, again with a higher order method. So the truncation error and the total error is reduced for those higher order approximations, but we still have to be careful because if h is too small, the round off error can dominate. So for example, for that fourth order, what we saw is we want h to be greater than or equal to 0.001, or 1 times 10 to the minus 3. And as I said at the beginning of this video, this conclusion generalizes to algorithms for differential equations and motivates the use of higher order methods. It's one of the motivating factors. There's other factors as well, but this is one of the reasons why we aren't just going to use a first order difference approximation. That is the simplest, but it does run into this round off error problem, and using higher order difference approximations yield more accurate results and are more computationally efficient. And that concludes this video.